Okay, everybody, thanks for coming to this status update of the HelenOS project from 2016. My name is Martin Dětský. Actually, this talk should have been presented by Jakub Jermář, but unfortunately he fell ill this week. Nothing serious, just an influenza, but still it was hard for him to make it to FOSDEM, so he asked me if I can jump in the last minute. I hope that this won't affect the quality of the talk too much. So let's start. Before I dig into the technical details, let me just refresh you. Some of you might not know what HelenOS is, so let's have a brief introduction. These are some adjectives that might describe HelenOS in a nutshell. It's an open source, general purpose, multi-platform, microkernel, multi-server operating system designed and implemented from scratch. And of course, you can download the sources and also some binaries at our website, which you see up there. Let's dig a little bit deeper. So open source means that our own code, the bulk of the code base has the BSD license, the new BSD license, and we also use some third-party components which we don't link directly to, but which we use indirectly, which are under GPL. General purpose, that means that we don't want to be biased towards any particular use case or any particular deployment. We want to create an operating system that is as useful for servers, desktops, embedded systems as for any other particular use case. Multi-platform. We currently support these 7 hardware architectures. This is our nomenclature, but I believe you can understand the abbreviations. You might remember from last year that I said 8 architectures. Nowadays it's 7. That's because we have removed one. We have removed the Spark V8, the 32-bit Spark variant, because we lost access to this special kind of hardware. It's being used mostly in the space domain, and also the emulators for this platform are very hard to get if you don't want to pay $1,000 a year. So to lower our maintenance burden, we have removed this architecture, but it might come back sometime later. It's a microkernel, obviously. I mean, yes, we are here in the microkernel dev room. Let's not talk about it. It's a multi-server. That means that the entire system is composed from fine-grained components. And if you are looking for a fancy buzzword describing this software architecture, it's microservices. And it really is. I mean, it's an operating system built out of microservices. And the longest adjective, designed and implemented from scratch, we really mean it. So in the core components, in the kernel, in the user space, we don't use any borrowed code. We design the system in a way we see the most fit in 2017. So our native API tries to reflect our ideas of how a modern operating system should be designed. We don't have a goal of implementing legacy APIs because we really believe that there is no better Linux than Linux. There is no better Windows than Windows. We don't want to be better Linux than Linux. We want to be the best microkernel operating system. On the other hand, of course, for practical reasons, for pragmatic reasons, from time to time we do need to port some applications and libraries from these legacy systems. So we do have an adaptation layer for porting, and we have some ported components, but this is a totally different topic. So this is an image that you probably aren't able to read in detail, and it's fine in such a way because I don't really want to go into the architecture right now, but it somehow shows the total composition of the system. It's not drawn in scale, so this is the entire microkernel, and these boxes might sometimes represent a few functions or even a single function. So this is really not a component, but it shows that even our microkernel has some internal structure. It's divided into the large architecture-independent part, which implements everything in the same way on all architectures, and there is a hardware abstraction layer, and then there is the part that is platform specific. It's roughly 10 to 15% of the kernel. So we really try to make our code base as generic as possible. And then this entire microkernel is shown here as this single component of the system, and then you can see the other components here, and even composed components like a file system composed component, which logically contains all the other primitive components inside of it. One note, for example, the networking is also decomponentized. So basically, if you know the networking reference model, the physical layer, link layer, transport layer, and so on, this is exactly the way how our networking stack is structured physically. So there is a separate component, separate task running in isolation from the other tasks in the networking stack for each of the networking layer. Just to give you some rough idea, in total, this is really not just the kernel, but in total, this is the size of the code base. This is some rough estimate of the work effort. Of course, this is totally wrong because the basic COCOMO model is not really suited for systems or system software, but it can give you some idea. And except of, let's say, 6 to 8 core developers, this has been developed in the course of some 24 master theses, 4 bachelor theses, 11 Google Summer of Code projects, and so on. So yeah, I should really mention our contributors here because we are eternally thankful for them. Okay, now you might think these are some crazy people who are just trying to reinvent the wheel, and this has no sense of really giving any attention. Let me explain it from a different perspective. The legacy operating systems, of course, they are working quite well, I would say, but their designs and APIs are in many cases broken, insecure. At the very least, they are morally obsolete, and that doesn't necessarily mean that everything is wrong with Linux, or that there is no hope of taking inspiration in principles or in implementations that have been around for many years. I have spoken about this topic 2 years back. But many things can be designed in a better way with current software engineering standards and principles, by thinking out of the box, by not implementing yet another Unix, by not trying to reinventing Linux or creating new Linux. And also, if I can slightly separate from my respected colleagues from other microkernel systems, we also think that it's important that we write the bulk of our system core components ourselves, that we don't import drivers from Linux using some device driver kits or rump kernels or whatever, because we are really afraid of Franken components. We don't want them. We want our components to suit our architecture, not to somehow glue them together using adaptation layers. If you don't get my idea, I'll show you these 3 pictures and let them think for a few seconds. So we don't want this. We want a nicely designed and engineered operating system. Okay, let's move on. There's also another issue with borrowing components from other systems, which we would really like to avoid, and that's the maintenance burden of these forked components. So once you fork something which is external, you basically create what Jakub Jermáš calls software fossil. So it's a snapshot of the code which the upstream is no longer required to maintain or to update. You are required to do it, and this creates the possibility of you forgetting or not managing to backport security fixes, new features. Sometimes you have to deal with diverging licenses and all this kind of stuff. So the HelenOS mainline, the microkernel and the core components, they are always fresh. They are always working in sync, and they don't age. While the HelenOS Coastline repository, which contains the ported software I have spoken about, they tend to do this, and this for us really shows the difference between creating the system in our own image and between porting some Franken components from other systems. Because the Franken components, they don't follow our basic development principle to design something, then implement it, then run some verifications tests on it, and then reiterating by learning from our own mistakes. Let me do a short intermezzo here. We would really like to cross-pollinate. I think we try every time we can. So last year, Jakub Jermáš has created this website, microkernel.info. And the idea behind it is really to join our forces with our fellow microkernel friends with other projects. It has been inspired, by the way, by the website unikernel.org from the unikernel community, and the purpose is the same. So it basically lists in alphabetical order the currently alive and progressing microkernel operating systems. Everybody can be included. I mean, there are no hard criteria for being accepted. There's just a brief overview of each of the systems and a link. Of course, the unikernel guys, they went already a little bit further, so their unikernel.org website also contains some tutorials and some other helpful materials. We can also have it. We can also move in that direction. No problem with that. Nobody just did it. So again, your input from everyone here is more than welcome. Really, the purpose is to create some quasi neutral ground for our own microkernel advocacy. Of course, it won't be totally neutral ever, because everybody is somehow involved in some of these systems, more or less. But we can at least try. And if I can even say so, we have also the common enemy, right? So we can join forces. Well, that was really more like a joke, but I mean, I would say that we are more friends with the unikernel guys than we are with the monolithic kernel guys. Let's put it in that way. So again, please, any contributions are welcome. And the other suggestion for cross-pollination, we have already discussed this in the mailing list of this dev room. We would really like to apply for this year's Google Summer of Code as an umbrella organization. I mean, HelenOS has some experience in Google Summer of Code. We have been accepted 3 times, and we were quite successful in GSOC. We weren't accepted 5 times. But still, Google Summer of Code is at least we see it as a very valuable thing for a niche software project, because it really widens the awareness or spreads the awareness of the project more than anything else, I would say. So the ratio between the acceptance and non-acceptance, we don't know why we were accepted in these years and weren't accepted in those years. I mean, obviously our application was consistent. We didn't just screw up in the other years. Everybody knows that Google is not sharing its internal criteria for accepting projects into GSOC, so we don't know what's the problem for them. But we think, or at least we have a hypothesis, that one issue might be that there is simply just an abundance, or that there are too many operating system projects in general applying for GSOC. I mean, there's Linux, FreeBSD, NetBSD, OpenBSD, Ilmos, all you can have it, and probably they don't quite distinguish between the monolithic systems and microkernel systems. So maybe, I really believe that we should at least try, even if we don't succeed, an umbrella organization for all microkernel systems might help in this way. So we had already some, I would say, positive feedback from some other guys. So if somebody wants to add something to it here, let's discuss it here or during the dinner. Just think about some of the technicalities. So the deadline of the application is approaching quickly. We can manage it, but we have to really agree on this sooner than later. So first question is, who should fill in the application? Are there any volunteers? So we are volunteering. Yeah, we have some experience, so we can give it a try. I mean, obviously we won't do it like copy pasting for our own application, but we will try to give it some twist. Again, any input is more than welcome. Where the idea page for this organization should be hosted, I mean, I really think that the microkernel.info is the perfect place to host it. Again, please do send us your topics, your ideas for GSOC if you want to be included. I mean, the more topics, the better. That's probably the key. If you need some inspiration, I can send you links to our previous ideas pages, even from those years that we were really accepted. So you can see some working example. And the last question I would really like to ask here to my colleagues: should we discourage individual applications from the individual projects? What's your opinion on that? Anybody, I mean, anybody who wants to join this, if it's okay or not.
So we haven't planned to join Google Summer of Code. I think we have tried once or twice, but they are rejected, and for reasons that I don't know.
Nobody knows.
So we did not consider to apply another time. So I would like to know your experience about. You say that it's very valuable for HelenOS, and what I would like to know is how sustainable is the effect. So is this obviously that Google is paying money for people working on specific topics, but that's just a kind of one shot of money. But the question is does it suffice to ignite the interest of those people so that they stick to the project, or do they just do this kind of 3 months of work and then they disappear magically? Because then I would say the investment of mentoring is not so efficient, because it has not a sustainable effect. So what's your experience?
So my experience, there are two layers in your question. The one layer is whether it is worth the short term investment. I would say still yes, because the usual, at least in our case, the usual GSOC project creates roughly the same amount of code as a master thesis. But a master thesis can take a year or 2 years to be finished, and sometimes even never gets finished. In GSOC, the same amount of work gets done by the student in 3 months. So if it succeeds, it's quicker. If it fails, it's also quicker. So from that point of view, it's I would say it's worth the investment. And you probably also do some supervise some master thesis from time to time, so you know what I'm talking about. And about the long term, whether it really ignites some students to stay with the community, yeah, I would say the return ratio is not very high. It's something, in our case, something like 10 to 20% of the students. But it's still more than zero, meaning that these students or these people would not know about us without participating in GSOC. So it's a net benefit still. Even if it's just marginal, it's a net benefit. So I mean, if this should fly, all that is needed is to come up with, I don't know, 3-4 interesting projects from each of the participating projects in under this umbrella, which is probably not so hard. I mean, you should probably have some ideas flying around for other purposes. So just putting them in some shape that is somehow acceptable might take, I don't know, 2-3 hours, and so we will see. Of course, I cannot guarantee anything, but I really think we should try. And if I may answer to my own question, I think we should not discourage the individual projects for applying still, because, I mean, we don't know what the Google's criteria are, so they might see it as a problem that they are trying to have more stakes in the ballot, or maybe not. We will see. We can even try 2 years in advance in different settings and hope that we are not fighting an oracle which changes every time. We will. I mean, we can just try. So if somebody is in, please email me or email Jakub. We will just make it happen somehow, and everybody is welcome.
Don't get me wrong. I like this idea because you mentioned this word cross-pollination.
Yes.
And so far, I think after all these years, this really hasn't happened so much between our projects. So we had once this kind of project where the Spartan kernel was brought together with Gino, or at least attempted. So I like this as a chance to build bridges between the projects in some way. So maybe this
is not even necessary. I mean, the umbrella organization is really something that covers multiple individual projects. I mean, GNU is doing that. I mean, the GNU is participating in GSOC in many years as an umbrella organization for various GNU-related or even GNU-unrelated projects. So this is just a single organization that supports. Yeah.
I think I'm with Apache Software Foundation, and I think I really agree with your point. So what a lot of times happens is Google Summer of Code looks for formal organizations. So it can basically, and I don't know why, but maybe it's because they like sort of how the money is managed, or the guarantee that it won't be some random people or whatever.
Yeah.
But if you have a non-profit in the United States, it's actually much easier to get your projects accepted. On top of that, again, in ASF, the trick is that ASF always gets accepted because we're sort of one of the known open source organizations, and then you can basically have as many projects within the ASF umbrella as you want.
Mm.
So it's actually
exactly.
very beneficial.
Yeah, that's my point exactly. So perhaps we should skip this discussion to the offline time, but I just wanted to show this here. And again, everybody is welcome. So now let's move to the real status update of HelenOS. We are talking about the year of the fire monkey, which somehow coincides with the period from last FOSDEM to this year's FOSDEM, so that works nicely. Some general observation. Yeah. there is slightly less activity on our side than in previous years, mostly because the core contributors are somehow distracted now, me included, so we don't have so much time to contribute to HelenOS. Also, there are much less students, so we didn't participate in Google Summer Code, we didn't participate in ESA Summer of Code in Space, and there were only 2 master theses running compared to, say, 6 or 8 in the previous years. And I would say we are somehow plateauing. Really, this is the key message here. Of course, I cannot claim that HelenOS is perfect and finished. That will never happen. But it's finished from some perspective that we don't lack any major subsystem now. So we have networking, we have sound, we have USB. You name it. So there is no big chunk of code totally missing. So we are more switching into the phase of optimizations, refactoring, and so on, and that's probably not so attractive to many people. So that's my explanation why the output is smaller. This can be also illustrated on our traditional HelenOS camp, which is our hackathon, which has been done since 2005. So not so long as the OpenBSD's hackathon, but also for a long time. And this year, only some 3 developers participated. There were some overlaps, but yeah, on average 3. So this is quite poor. But we managed to implement something. So what we are currently working on, or what has been done recently, I was hoping to make a release before FOSDEM, but then Jakub fell ill and I had to write those slides and so on. So I didn't manage, but I might manage tomorrow. So it might be a FOSDEM release. Yay. So we have done some improvements on our Spark 64 support for Sun4U hardware. This has been jointly done with parallel developments in QEMU. So we are very. It's hard to quantify, but we are somehow close to be really able to run HelenOS on Sun4U in QEMU as on physical hardware. This has been linked with somehow generalizing our user space serial console code. So previously there were different ways how to use user space serial console on different platforms, and this has been somehow unified. We have a simple installer, which is non-interactive, maybe a little bit dangerous. It tries to not to overwrite anything on your local hard drive, but I will still not really run it without consideration. And it's basically a first step into really deploying HelenOS as a permanent operating system. So it currently targets QEMU and works on these 2 platforms. But it includes a reproducible build of grub. So we are really pushing this idea that our builds should be reproducible, that you should be able to run a single command on any platform, on any guest system, and this single command should create the same binaries, the same composition of components, and so on. And of course, the grub is one of the components that we don't link to, but we use as a bootloader. So we build it also. Finally, we have USB 2.0 support that has been in writing for 3 or 4 years, because one of the original authors of our USB stack decided that he would like to rewrite it completely, and he more or less did with some input from us. It not only enables USB 2.0, but it also opens much easier path to USB 3.0 and so on. We have optimized our processing of hardware interrupts in user space drivers. Originally, there might have been a large overhead if the device was generating too many interrupts in a single unit of time, because each of the interrupts was translated to an IPC message, and for each of this IPC message a new worker fibril was always created and then disposed, which created the overhead. So now it works in much more optimized way. Basically it's coalescing the calls somehow so that the fibril, the worker fibrils do not have to be created and destroyed every time. There's again much more to do here. Some fibril pooling might help even in different workloads. We have improved our dynamic linking, especially with the respect to the thread local storage handling, and we finally have dynamic linking enabled by default on AA32. So if you compile HelenOS for x86, it will be created, dynamically linked binaries will be created by default now. Another small improvements which is somehow related with the thread local storage. For a very long time, from the early beginning of HelenOS, we had this ugly special syscall for setting the TLS base address on x86 and on AMD 64, basically because this sets the FS or GS register, the selector, which is then used as the pointer for the base address for the thread local storage, and this cannot be done, or this was not possible to be done from user space. So there had to be some way how to deal with it, and we really didn't like it. Of course, it's a ugly thing to have this stupid syscall just for the sake of one architecture. So our current solution is to have a different configuration of the thread local storage that can live with a static configuration of the GS and FS segments, and only a pointer in this thread local storage structure needs to be changed, and then this is used as the basic address for the thread local area. There is even a better solution. We have discussed it with Jakub Jermáš, how to do it in an even more elegant way. There are these two new instructions since Ivy Bridge, which can be used to set these two registers, or not these two registers, but basically the values of the segments, or the base addresses of the segments from user space. Of course, on older CPUs this does not work. So how to do it in a generic way? Well, it can be emulated. So if the kernel receives an exception that there is an invalid instruction and it's this particular instruction, it just can be emulated. In theory it works nicely and it's elegant, but the performance is worse than our current implementation with this GCC specific option. So we are still thinking about what should we do with that. And of course we have been doing, like I already said, a lot of code refactoring. We have fixed many bugs that have been discovered by verification tools. We are still on the bleeding edge of the GCC tools chain, and we have helped to discover a regression in QEMU 2.7.0 on ARM. Yeah, RISC-V, I know. I have promised that this should be ready in 36 hours last year, and frankly I really didn't spend the 36 hours to do it, so sorry, it's still not. There is some skeleton code in the main line, so at least you can try whether the RISC-V compiler is still compiling the sources, but it's still not. It's booting, but it's not doing anything past the initial kernel initialization. if I may have one small excuse for that, there have been some changes in the privilege specification of RISC-V during the year, and there have been also changes in the Spike simulator, which is something like a reference implementation of the RISC-V platform. And some of these changes were not explicitly tracked and documented. So it was really a bad surprise that you compile the code, run it, and then you have to debug it for an hour to really understand what went wrong, why it's not working as it used to work a week ago. And two final items I would like to mention a little bit in more detail. It's a service manager and user space pagers. So we have where is he? Yeah, there he is. Michal Koutný, my former master student, who implemented the service manager for HelenOS as his master thesis. So, yeah. I have already mentioned the term microservices. So naturally, a microkernel multi-server operating system is composed of services. But this is an overloaded term. So we are talking about the system services now, like the microkernel servers. And there are also, logical services, like if you run an HTTP server or, I don't know, NFS server on your machine, that's a different kind of service, not necessarily tied to the architecture of the operating system. So this service manager for HelenOS tries to combine these two entities somehow together, so to have a unified look on the microkernel services and on the logical services. It is remotely inspired by System Management Framework or Systemd, please don't kill me. Let's move on. So basically there are two new components. One is doing the dependency resolving. So it basically starts and stops the logical services according to some dependencies. These dependencies can be either explicit, so they can be specified in a configuration file in some declarative way, similar to what you might know from other system management frameworks. And of course, there are those implicit dependencies that are built from the architecture of the composition of the microkernel services. So this is basically for more or less for free, because it used to work without this new component previously. Now it's just integrated into one package. And there are some unit types, so like the individual service instances that can be either a service, meaning a process, a mount point, a configuration, or a target. And then there is the Taskman service, which basically is monitoring the life cycle of the services and provides an monitoring API. So it manages the logical relationship between the physical processes, because there is no such thing in HelenOS as a parent and child process. So this has to be created This has to be created anew, and this service can later be used for restarting, for example, if a service fails or something like that. So it's dependency part and lifecycle part. And the final implementation piece that has been done is are the user space pagers. This is one thing that in which HelenOS architecture differs from I would say most of the L4 family operating systems, which really focus on removing all memory management from the kernel except the privileged parts like accessing the page tables and managing the TLB. In HelenOS we have decided to have a different approach, to have a slightly more traditional architecture of the memory management with a kernel frame allocator, a kernel heap allocator, which is a slab allocator, by the way, and a virtual address space manager. It's still mostly mechanisms, so there are almost no policies in the kernel, except maybe some basic algorithms like single fit and so on. Our motivation for doing or for implementing memory management in this way was that we believe that it's still a single point of failure. So even if we push it out into user space, the kernel would not survive, or even for its own purposes, if the memory management service or the memory management server would fail in user space. So in that case, we don't see a major point for not having this in the kernel itself. So originally there were 3 address space area backends for mapping physical memory for devices, because also the kernel needs to have support to the hardware, at least for the timer. Then for anonymous memory, that basically is used to give memory to the user space tasks, and for mapping ELF binaries, because the kernel during bootstrap needs to run some initial binaries, so it needs to be able to access that structure in some structured, intelligent way. And now there is another backend which can forward page faults to user space, basically. So the current implementation is really quite straightforward. There is a task that needs to access some memory which is being provided by some other user space task, and it can be anything. It can be, for example, the virtual file system providing memory mapped files. So each of these tasks has its virtual memory map in the kernel, and first the new address space area is created by the client, and it's a special kind of virtual memory area which with that user pager. Then this creates a dedicated IPC connection to the server, and the server creates its internal representation of this client, of this request. Then if the client accesses the memory, it touches the memory within that area that needs to be served by the pager, it naturally creates a page fault, and this page fault is forwarded to the pager as an IPC message, while the pagee is blocked. And now the pager asks the kernel to give the client some part of its address space. So it basically answers the IPC call by this return value says that it's okay to provide the memory to the client, and supplies its virtual address of the piece of memory that it wants to provide. This virtual memory is then translated to the physical address by the kernel, and this physical address is then mapped to the client, and the client is woken up, and that's it. I mean, now this dot or this page is alias to this page. So it's a really quite straightforward implementation. We have some additional ideas how to make it in a more generic way in the future, but just for the purpose of implementing memory mapped files, this works pretty nicely. So, any plans for this year, for the year of the fire rooster? Yeah, we have some research papers in the pipeline. We would like to finish them and submit them. I would really like to finish the RISC-V port. We have ongoing cooperation with the CZNIC, that's the Czech National Domain Registry. They have this nice project called Turis Omnia. You might have heard about it even on last FOSDEM and on this FOSDEM. So it's basically a very well-designed home or small office router, and we would really like to fine-tune HelenOS on this particular piece of hardware and then start some interesting collaboration with them. We would like to switch to the annual release cycle, just because we are no longer in the phase that we are waiting for this major subsystem to be written, that major subsystem to be written. It's probably easier to take inspiration from the Genome guys, where they simply release often with new, smaller, perhaps smaller updates. And we have already done some IPC optimizations, and again, now it's time to really dig in deeper and to, for example, implement some weight-free algorithms to improve the overhead and so on. So that's basically all from me. Thank you very much for your attention. And if there are any questions, I will be happy to answer them, and we can still discuss the GSOC stuff if there is some interest. Okay, maybe later. Thank you.